Welcome back, curious people. Today we will talk about the delta function on our way to understanding the delta potential. By the end of this video, you'll be able to evaluate integrals and statements that use the delta function insofar as understanding what it's trying to ask of you explicitly. The delta function is used throughout the landscape of theoretical physics, and of course quantum mechanics is highly theoretical, so of course we're going to see it. It is known as a delta potential, and they have some really weird consequences to them. But what we have to first understand is what is a delta function. And so let's pay attention that if we're going to evaluate the integrals that are seen here, they all involve this little curly d, which is the delta, and they all are shifted, by some amount here and here, and the integrals all have various limits here. The question still remains, though, what is the delta function? Well, mathematically speaking, the delta function is not really a function, although it's defined piecewise as such, where it's 0 where x is not equal to 0 and infinity where x is 0. This is absolutely bonkers in the sense that it makes no functional sense insofar as passing a vertical line test. So many mathematicians and mathematical physicists will call this more of a generalized function, a fonctionnel, or they will even go so far, and this is primarily what they live with it as a distribution. And as a distribution, this means that the delta function technically lives in the integral, as we see here. This definition in the piecewise sense is coupled with this integral definition where the area under all of the space is equal to 1. Okay, what this tells us about the function is that we have a infinitely small width and an infinitely high height. And so this is going to lead to some interesting things as we start multiplying by constants and shifting it around. And that's what this whole problem is based on. So let's dive in. Okay, so now that we have kind of a little background into the delta function, how is it that we actually evaluate these integrals? And it's actually really simple. All of these functions or integral equations, integral expressions, need to use the shifting property of the delta function, which is what we see here, meaning that if I take some function and I multiply it by the delta under the integral, or even in just without the integral, what we see here is that we shift the function to the point where the delta is centered. Okay, this is important because the delta is equal to 0 everywhere that is not at x equals a. Okay, in the original definition, this was a equaled 0, so we had x at 0. But here, if x is not equal to a, it's 0 everywhere, so the function doesn't exist unless it's at the point of f equal a. And that's what we see here in the shifting property or sifting property. Different books call it differently, but our goal here is to understand that we need to find out by what factor this a is that we know that the function is shifted by. So for our first example, as you see with the color code, we have a plus sign here, which goes against what the form says here, but we know that a plus sign is nothing but two negatives. Okay, so doing this is going to be very good for you because it makes you practice form matching, but also if you're already used to that, and this video is probably not for you, but nonetheless good practice. The point is, now we have this as our a factor, -2 is our a factor. So based on this form, we simply have to evaluate the integrand that is tagging the delta function. We have to evaluate that at f of a. So we do that here, and we see that we just plug in -2, -2, -2 for all of the x's in the polynomial, and they evaluate down as such, and that equals -25. Now this works because the integral of the delta function is 1. So if I shift this thing with the u sub, meaning that I take x minus a and then solve it for u and then shove x at a into the function, then at f of a, I have f of a times the integral of the delta function, which is 1. So that's why this property holds, and we don't have to worry about integrating or antiderivatives with this thing. We just simply have to plug in the value of a into this so long as the bounds allow it. Notice that -2 falls between +1 and -3, so we're good to go. A lot of talk about these little technicalities, but they will come up again at some point. Alrighty, so since we've seen one example, let's go ahead and chug out the rest. We note here that we just have delta of x minus pi, so we're shifted by an amount pi, no big deal. Pi is also between 0 and infinity, so we're good on that account. And we see that we can just plug it in. So cosine of 3 pi plus 2, that just yields -1, since cosine of 3 pi is on the 180-degree line. So that's -1 plus 2, that gives us a +1. Check, easy enough. The next one is 100% going to come up again in some form, and you're going to be upset with yourself if you do a bunch of work only to realize that the integral is 0. Meaning that, notice that our bounds on the limit is +1 and -1. But our function is shifted to the right by an amount 2. So we see here that x minus 2 is equal to 0. That's where the delta function is centered at. So if we push it over, we see that the function is centered at x equals 2. Okay, that's easy. But realize here that 2 is not in the bounds of the integration limits. It's not between -1 and 1. So what this tells is that the delta function is outside of where we're integrating from, and that means that it is equal to 0, and so we take the integral, multiply it by 0, and we end up with 0. All because that delta function is shifted elsewhere. This is such a useful tool, and it is used throughout an entire branch of signal processing and physics. It's just used everywhere, so it's best to get used to these things and comfortable with them. We'll also see a cool theorem coming up soon about what happens when we multiply by a non-unitary measure, so a non-1 measure on x. So we can generalize this property with the scaling property, and we'll have both that we need, and we'll be good to go. And as always, until next time, happy learning.